Scientists are sounding the alarm. Somewhere beneath the ocean floor, the ground has been coiling like a spring. And it has been doing so for centuries. The next mega-earthquake isn't a what if, it's a when. And here's the part nobody talks about. The shaking isn't even the worst of it. The real catastrophe arrives after the ground goes quiet. And when it does, it won't just threaten the country sitting above the fault. It could reach shores thousands of miles away, before most people even know what's coming. Deep beneath the seafloor east of Hokkaido, Japan, something has been building for over 400 years. Tectonic plates grind together in a slow, relentless collision. And every year that passes without a release, more energy gets locked in. The seismic data is now showing researchers something they can't ignore. The pressure beneath this stretch of ocean has reached the threshold for a magnitude 9.0 earthquake. Not a 7, not an 8, a 9. On the scale we use to measure these things, that's not a step up. It's an entirely different world. It can flatten infrastructure in minutes and erase coastlines in seconds. The pattern makes it worse. Mega-thrust earthquakes have struck this coastline roughly every 340 to 380 years. The last one hit in the 17th century. Do the math. The region isn't just due, it's overdue. The probability of a catastrophic event in the next 30 years now sits at around 90%. Japanese authorities have stopped asking if. They've started building around when. The country runs one of the most sophisticated early warning networks on Earth, a system that the instant it detects the first seismic signal, fires alerts to every phone, television, and radio in the country. Trains stop automatically. Gas lines seal. Elevators drop to the nearest floor and open. All of it in the seconds before the worst shaking begins. Because when this fault finally breaks, the waves it sends across the Pacific could still arrive with devastating force thousands of miles away. Just as they did when Japan's 2011 earthquake sent surges crashing into the California coast. Now shift your gaze west. Beneath the waters of the Sea of Marmara, directly below one of the most populated cities on the planet, something is stirring. A new generation of seafloor mapping has revealed a vast fault system running beneath the Mediterranean. And what researchers found is changing everything we thought we knew about earthquake risk in the region. The Mediterranean sits at a geological crossroads. The African plate, the Eurasian plate, and the Anatolian plate are locked in a permanent slow-motion collision. The crust here is thinning over time, and thinner crust cannot absorb stress the way thicker rock can. Pressure builds, energy accumulates. Istanbul, home to more than 15 million people, sits almost directly on top of this system. For decades, the fear was a single catastrophic rupture running coast to coast beneath the sea. But when scientists ran 3D computer simulations spanning more than 10,000 years of earthquake cycles, feeding in real temperature measurements, sediment data, and rock friction profiles, they saw something different. The fault doesn't behave like a zipper, ready to burst all at once. It behaves more like a row of ceramic tiles, cracking section by section. Deep beneath the seafloor, rising heat causes rock to flow, rather than snap, acting as a natural break that limits how far any single rupture can travel. No simulated event in 10,000 years exceeded magnitude 7.3. That sounds reassuring. It isn't entirely. A 7.3, directly beneath a city of 15 million people, especially followed by a second strong event in quick succession, can collapse neighborhoods, fracture water systems, and trigger tsunamis in a sea ringed by dense coastal populations. The last major rupture in this section happened in 1894. That's over 130 years of accumulated strain, building silently beneath one of the world's great cities. In early 2025, something remarkable happened in the Aegean Sea. In just a few months, more than 28,000 earthquakes lit up the seismic network around Santorini. Most were small. Some reached magnitude 5, strong enough to crack walls and prompt evacuations across parts of the island. But what made this swarm different was the way it moved. The epicenter didn't stay put. It migrated steadily northeast toward a submarine volcano sitting about 5 miles offshore. Scientists recognized it immediately. Magma was on the move. Roughly 80 billion gallons of molten rock, enough to fill 120,000 Olympic swimming pools, had surged upward from 11 miles beneath the seafloor. It rose fast, then stalled just 2 miles below the ocean bottom. It didn't erupt. It just waited. This episode rewrote the understanding of volcanic swarms. Magma can fracture miles of crust, reshape underground reservoirs, load the system for a future event, and never show its face. Not yet. Now, Kaniskay, can you lift a truck with your bare hands? The ocean once tossed 700-ton boulders across the African coastline like gravel. Geologists found them, ran the numbers, and concluded that only a wave approaching 800 feet tall could have moved them that far that fast. The 2011 Japan tsunami produced waves 133 feet high. The 2004 Indian Ocean disaster, which took more than 200,000 lives, was smaller than that. Both are already the stuff of nightmares. Now imagine something 10 times bigger. The culprit behind that ancient monster wave was not an earthquake. It was a volcano that fell apart. Off the West African coast, an island called Fogo had been building itself from the seafloor for millions of years. Eruption after eruption, layer after layer, stacking upward. But the heavier a volcanic island grows, the more it compresses the magma chamber below it. When the pressure builds past what the structure can hold, gas and heat push toward a breaking point. At some point in the ancient past, Fogo lost a flank the size of 10 Mount Everests into the Atlantic. The wave it produced could have buried the Statue of Liberty 3 times over and destroyed an island more than 30 miles away. In 2018, Anak Krakatau repeated the process on a smaller scale, losing a chunk of itself during an eruption, generating a tsunami. Survivable. But a reminder that the mechanism is still running. Hawaii, La Palma, parts of the Caribbean, all sitting on the same volcanic architecture. Steep flanks, loose foundations, magma chambers quietly pressurizing from below. Your favorite island getaway might be paradise. It might also be a spring wound very, very tight. Here's where science fights back. In the most unexpected way, running across the ocean floors of the world are nearly 1 million miles of fiber optic cable placed there to carry internet data. But scientists discovered something extraordinary. These cables feel earthquakes. When the ground shakes, the light pulses traveling through the cable are disrupted in ways that instruments can read. By analyzing those disruptions, researchers can detect seismic movement in real time across thousands of miles of seafloor that would otherwise be impossible to monitor. For a region like the Mediterranean, hidden faults, active submarine volcanoes, packed coastlines, this technology could deliver the one thing that saves the most lives. A few seconds of warning. Seconds sound small, but seconds let trains stop. Seconds let gas lines close. Seconds let a person step away from a window. The ground beneath our feet has always been moving. It moved before the first city was built. It will move long after we're gone. We cannot stop tectonic plates. We cannot cool a magma chamber. But we can learn to read the signals the Earth is already sending. The slow creep of a fault, the migration of a swarm, the bending of light through a cable on the seafloor. Nature wrote the rule book. Science is finally learning to read it.